Today, we will be going through on how we approach and tackle the Spurbank Russian housing market challenge on Kaggle. Housing cost has always been a significant expenditure for budget considerations, and in the context of Russian housing market, the problem is that there are many uncertainties in the economy that can affect housing prices. In this competition, we were tasked to develop algorithms that can predict relative prices that will hence allow Spurbank to provide more certainty to their customers. Here are the challenges we face. Firstly, there were errors and missing values in the dataset. Secondly, depending on the model we choose, we will need to decide on how to deal with categorical columns. Thirdly, due to the complex and large dataset, it was difficult for us to identify the important columns for training the model. This also made choosing a model a challenge for us. The first two challenges will be discussed in the data cleaning stage, while the last two challenges will be discussed in the feature selection stage.
Firstly, we analyzed the data to have a better understanding of what needs to be done for data cleaning. There were a couple of steps we took to handle the data cleaning. For the build year column, there were two rows with values which were obviously wrong, namely where build year equals 4965 and 2005-2009. We simply removed these two rows from the dataset since these wouldn't affect the model much. Next, we had to perform encoding on categorical features to tackle the problems of having categorical values. We tried ordinal, one-hot, and target encoding. Ordinal encoding involves encoding features such as ecology into ordered numerical values representing the different conditions. One-hot encoding was applied to product type because the values were simply labels with no order to it. Target encoding was used on sub-area where the encoded categorical values would be represented by the average price dot for that sub-area. Eventually, we decided to use only one-hot encoding because it produced the lowest error. Lastly, we also tested dropping rows containing named values for categorical columns. However, the model performed better when such rows were not dropped, so we kept them instead. Moving on to feature selection, we now attempt to identify the columns with greater importance. Shared values are values of importance assigned to each feature in a model, and they indicate how a feature will affect the choices the model makes or predicts with the usage of game theory. The values were used for us to determine the top features of our XGBoost model, which we chose for the property price prediction due to its efficient and good performance on complex datasets. Finally, with the help of Shape Library's tree explainer class, the XGBoost model was explained and analyzed, helping to identify the key features. The top features of our model were then generated, as can be observed from this crop chart of the top 50 features. Initially, we fill in the missing values of each column with the mean value of that column to tackle the problem of missing values. Now that we have our top features, we take a more granular approach to fill in the missing values for the columns of higher importance. For max floor, build year, and state, we fill in the missing values with the median value of each column respectively, grouped by the properties in the same sub-area. For example, if there is a row with missing value in the max floor column belonging to the BB Revo sub-area, we will fill it in using the median max floor value for properties belonging to the BB Revo sub-area. For floor, we simply fill in the missing values with the max floor value of each row respectively. For num room, we split the full SQ values into different ranges and calculated the average num room values for each range. Then, we fill in the rows with missing num room values using the calculated average num room value depending on which range of full SQ values the row belongs to. Finally, for Kitsch SQ, we calculated the average Kitsch SQ over Live SQ proportion, grouped by sub-area, and fill in the rows with missing values using the Live SQ value multiplied by the Kitsch SQ over Live SQ proportion, depending on which sub-area the row belongs to. Now, Yuqing will explain more on the models that we have used.
Now, I'll be covering the models we used for this competition. There are two models that were used. The first is XGBoost. XGBoost is an optimized distribution gradient boosting library made to be highly efficient, flexible, and portable. XGBoost provides parallel tree boosting and it splits tree level-wise. Why was XGBoost used? This is because of its gradient boosting algorithm capacity to handle outliers effectively. This algorithm exhibits robustness to outlier data points, thus ensuring that the presence of extreme values in the dataset does not influence the model's prediction negatively. This is important since our dataset contains many outliers, but we were unable to simply drop the rows containing them. Otherwise, it would greatly reduce the dimension of our dataset, and that will affect our model's training. It supports parallel tree construction, which makes it efficient, and it is consistently one of the top performing algorithms in terms of accuracy. This is due to its ensemble learning approach that combines results from multiple individual trees and translating to accelerated learning and enhanced model accuracy. XGBoost also works well with large dataset compared to other machine learning models, which is applicable in our case since the dataset we were given is considerably large. Another model that we chose to implement was the LightGBM model. LightGBM is also a type of gradient boosting machine that uses an ensemble of decision trees to make predictions. It is capable of handling large data and supports parallel tree construction and feature processing. It splits tree leaf-wise, unlike XGBoost which splits tree level-wise. Since LightGBM splits tree leaf-wise, it utilizes a technique called exclusive feature bundling that is a near lossless method to reduce the number of effective features. Like GBM is a histogram-based algorithm that performs bucketing of values, resulting in faster training speed and accuracy. This algorithm also reduces memory usage. Not only that, the utilization of gradient-based one-side sampling also allows the model to retain instances with large gradients and perform random samplings on instances with smaller gradients, causing it to be more accurate. Thus, we decided to train this model on our dataset as well.
After deciding on the models to use, we then had to optimize and train them. This was done through multiple rounds of tuning the hyperparameters and identifying relevant features to use. The first challenge we faced was finding an efficient way to optimize the large number of parameters we had. The standard grid search approach just wasn't going to cut it. Thus, we moved forward with another library, Optuner. Optuner offers an efficient search of parameters through cutting-edge algorithms. It's also extremely easy to use. For example, we simply provided the parameters that we wanted to tune as well as the range of values to test out. In less than 20 minutes, the optimal values would be returned, which was way faster than grid searching. Next, with the initial optimal parameters identified, we then re-evaluated the top features. In our presentation, we will only be showing results of light GBM, but note that these tests were conducted for both models independently. Throughout most of our experiments, we will be using a 5-fold cross-validation. This helps to improve the model evaluation as k-folds provides a more robust and reliable estimate of a model's performance. Furthermore, it ensures a fairer comparison when we are trying to identify which features to use as models are tested over the same range of subset of data. The top 100 features were evaluated. The plot here shows the average sharp values for each feature through the 5-fold cross-validation. To further improve the features selected, as we did not want any noisy features to hinder our model performance, we iterated through the list of top 100 features and recorded the average RMSE score. In the plot shown here, we selected the top 65 features. Finally, with the optimal hyperparameters and the number of features, we then retrained the model. In this, a 10-fold cross-validation was carried out instead. Similarly, we recorded the RMSE score for each of the folds. However, we decided to choose the model with the median RMSE score instead, as we noticed that picking the lowest RMSE score does not always result in the best prediction. This could have been due to overfitting relative to the median model, which might have been more generalized. As mentioned previously, several rounds of this was conducted to continuously improve the model and build upon what was previously tested. Ultimately, this was our final hyperparameters that we used. We managed to achieve a rank of 1288, which was around the 60 percentile mark. However, we wanted to do better and further improve the model.
In our attempt to improve the model, we dove into Kaggle discussions for inspiration. Most teams provided a general description on how they identify and clean the dirty data present in the dataset. After careful examinations of various data cleaning strategies, we decided to adopt one that was suggested by a couple of teams at the top of the leaderboard. These are the features involved in the data cleaning process. The methods listed here mainly tackle the logical side of the features. For example, live square is the living area of the apartment in square meters. We impose a condition that it's not practical for the living area to be under 5 meters squared. If the condition is met, the value for live square is replaced with an NAM value which can be processed by either XGBoost or light GBM. Different conditions are imposed on the features here, and the ultimate goal is to ensure a logical distribution of our data. Note that to maintain consistency in the model's prediction process, the train and test data are subjected to identical data cleaning modifications. Next, adopting the feature engineering method, we created new features that can capture deeper insights from the raw data. The most significant change we made is the model's prediction of price per unit area rather than the actual price itself. We believe that this change enables the model to better assess the value of houses. Finally, we identified a significant difference in the distribution of housing prices in relation to the feature product type. Product type consists of two distinct values, owner-occupied and investment. Our solution was to split the data based on these values and train our light GPM models separately. This allows the model to fine-tune their hyperparameters according to the different product type. The results produced by the model enable us to break into the top 10% of the leaderboard. However, given that we have two models at our disposal, we decided to use weighted model averaging to compile results. Weighted model averaging assigns a weight to each model, which represents its importance in the final prediction. We adjusted the weight such that it converges to a minimum public score. The final prediction nets us the position of 12 on the public leaderboard.
In conclusion, we did data cleaning and feature engineering on our dataset, and this helped improve the training of the dataset on each of the models, XGBoost and light GBM. We further improved on our methods by using weighted model averaging to create an even more robust and accurate prediction. This improvement led us to achieve our best possible position of 12 on the Kaggle leaderboards. Thank you.